Hello guys, welcome to Real Convenience Telecom Academy. This time we are moving a bit away from electric circuits and we are now going to capacitors. You might have covered this in your electronic course, but this time we'll be covering capacitors in more detail. From anywhere, at any time, and at any pace, and from any device. Let us enjoy. If you are new to this channel and if you are not new but you haven't subscribed, don't forget to hit the subscribe button so that you continue to receive more and more tutorial videos on your various courses at college or at university. As usual, my name is Motion Marufo and my email address motionmarufo60@gmail.com. You can also get in touch with me on +26371755866 if you want to have a chat with me. Insofar as real convenience is concerned, from the comfort of your homes or from the comfort of any place at any time and at any place, above all from any device, you are now studying capacity. And guys, let us enjoy. A lot of objectives on capacitors. Guys, you must be able to define capacitance and also to define capacitor. Then you must also be able to define farad, and farad is the unit of capacitance. Then we have got some common terms that are used in capacitance. You must be able to define them. Then capacitor action, you must be able to define how it operates or how it gets charged and also gets discharged. Then for capacitors connected in series and in parallel, you must be able to find equivalent capacitance or total capacitance. Then you must be able to also define characteristics or to state characteristics of capacitors connected in series and in parallel, as we did for resistors connected in series and also in parallel. Then capacitance is affected by many factors. You must also be able to state and to describe those factors. Then the formula for finding capacitance: C is equals to epsilon naught epsilon r, and A is area divided by the distance between the plates D. You must be able to use it or to calculate any of those parameters given some. Then you must be able to calculate flux density, electric field strength, capacitance, absolute permittivity, and some other terms that are related to capacitance. That is a duplication of common terms encountered in the study of capacitors. Let us enjoy. Introduction to capacitors. So far, we have covered, even in DC network theorems, we have been talking about resistors, and resistors. We've got an electric component which is very important in electrical engineering technology or electronics, and this is a capacitor. A resistor is different from a capacitor, or a capacitor is different from a resistor in that it does not dissipate energy, but it stores energy. In other words, if it gets charged, it stores that charge for a very long time, especially if it is a tantalum capacitor, and that charge can be retrieved later. Because of that, it is called a storage element. It stores and releases energy. In this presentation, we are going to analyze more important and practical circuits that involve capacitors. A capacitor is an electrical device that stores electric charge, and it does this for short periods of time. We've got some capacitors that are also able to store this electric charge for a very, very long period of time, especially the electrolytic capacitors with very low leakage. And like resistors, capacitors can be connected in series and also in parallel. We must be able to calculate equivalent capacitance for such capacitors. A capacitor, a resistor, resists or opposes the flow of electric charge. Electric charge is due to a current flow. Hence, that results in the production of heat, or in heat being dissipated. Capacitors store electric charge between the two plates. And this effect of storing this electric charge has got a much more significance not only within the capacitor, but also in the general operation of the electric circuit, that is the space surrounding it. And the effect in such space is called electric field. You covered electric field in the depletion layer. We will be talking about it in this video presentation most often. It takes time for us to fill a container with air water, and also it takes some time for us to pour water out of that container. This is the way a capacitor operates. It takes time to charge it, and it also takes time to discharge a capacitor. And this speed of operation has got a great deal of influence on the application of capacitors. And capacitors are used in a wide variety of electrical engineering, even in telecommunication engineering. So what am I saying? I'm saying just like resistors, capacitors are one of the three main components found in electrical system. The other component is an inductor. But for this presentation, we'll be looking at capacitor. Let us go. You remember passive and active elements or components. The capacitor is classified as a passive component, and it is designed so that it is able to store electrical energy in its electric field. Electric field simply refers to the field that surrounds a charged body, positive or negative. And we are saying besides resistors and inductors, capacitors are the most commonly used electrical components, and they are used in electronics, as mentioned, in electrical engineering, communication, computers, and even in power systems. We have at one time or another tuned from one station to the other. That component in our hi-fi systems which does the tuning of radio circuits or receivers is what we call a capacitor. It is also used as dynamic storage, memory storage element in our computers. You know, the DRAM, dynamic random access memories. What basically is a capacitor? A capacitor consists of two conductors separated by an insulator, or another word for insulator is a dielectric. So we have got the diagram of a capacitor. This is a plate, and the other side there is got a plate where the two conductors are connected to. And these two plates or conductors are separated by an insulator or a dielectric, and it has got a permittivity of epsilon. It has got also an area, as you can see, since it has got a shorter and a longer side. So basically, a capacitor is made up of two conductors that are separated by an insulator or that are separated by a dielectric. And we are saying the distance between this plate and this plate is d, and it is proportional to this or the width of the dielectric material. As alluded to in the previous slide, a capacitor generally consists of two conductors separated by a layer of an insulating material called a dielectric. The conducting surfaces are also known as plates, and they can be of any shape: cylindrical, rectangular, spherical, or even cylindrical shape. And as I said, its purpose is to store electric charge. You know what charge is, and how does it do that? By electrostatic stress in the dielectric. You find that some people refer to a capacitor as a condenser, but this is a misnomer, since we know that a capacitor does not condense electricity, but it instead stores it in its or in the electric field between the two plates or between the two conducting surfaces.
A capacitor has got schematic symbols, just like any other electronic and electric component. This is the symbol of a polarized capacitor, and it is an old symbol. The top terminal is the positive terminal, and this terminal is the negative terminal. It must be connected as such in an electronic circuit. Otherwise, if you interchange the terminals, it will be destroyed. So this is a symbol of a fixed value polarized capacitor. This is the symbol of a fixed value non-polarized capacitor, and it can be connected either way in an electric or electronic circuit. This is the symbol of a fixed value polarized capacitor as well, and it is a new symbol. It is replacing this symbol, and it has got a positive terminal, which is this terminal, and this bold terminal is the negative terminal. This is a variable non-polarized capacitor, and this is a variable non-polarized capacitor, but this is adjusted by a screwdriver. Hence, it is called a trimmer variable capacitor. So make sure you know this schematic symbol.
You might have met this word during your high school physics or combined science or even extended science, electrostatics. What is electrostatics? You must be able to define. And it is defined as a branch of electrical engineering which deals with electricity at rest or static electricity. We've got three types of electricity, and we've got one caused by a moving charge, and it produces current and a magnetic field. We know that a wire that is carrying current is surrounded by a magnetic field. Then we also have accelerated charges that produce radiation. For example, if we cause the charges to accelerate or to move very fast, we will radiate electricity in the space surrounding the medium that generates the radiation. For example, our antennas at our radio stations or TV stations, they make use of this accelerated charge, and this enables them to radiate electromagnetic waves into space. Hence we say accelerated charges produce radiation, and this radiation is beamed into space. Then what we are looking at in this presentation are called stationary charges, or charges at rest, or simply static charges. These static charges, they generate forces on other charges that are brought nearer them, and we say electrostatic is the study of these static charges and their associated effect. Let's have a look at laws of electrostatics. We encountered this at high school, and we say like charges repel and unlike charges attract. We are saying positive and positive repel, negative and negative repel, but negative and positive attract each other. Hence we are saying positive charged particle exerts a force of attraction on a negatively charged particle, and the same applies. A negatively charged particle exerts a force of attraction on a positively charged particle, and we are saying the space surrounding that charge undergoes some stress, and it exerts a force on any charge body that is brought near it. And the space origin, as I said, that surrounds that charge is called electric field. I think we are all aware of magnetic field. It is also known as electrostatic field or even dielectric electric field. And as I said, electric field or space is the space or field in which a charge experiences a force. It is also known as electrostatic field. We've got a positive charge and a negative charge, and you can see these lines radiating out of this positive charge are what we call electric field. So this is the space around a charged body or a charged particle. For a negative sign, please take note, the electric field is represented by incoming lines. The force between the two, we said we've got two laws of electrostatics, and we are saying there is a force of attraction between the positive charged particle and the negative charged particle, and it is represented by lines radiating from the or coming from the positive to the negative. But for like charges, positive and negative, they repel. Hence it is represented by these lines going out of the positive charge and moving away from each particle. This is what we call repelling, and this is what we call attraction. So these lines are representing electric lines of force. So we are saying by convention, the direction of these lines of force at any point is the direction along which a unit positive charge placed at that point would move or tend to move. The unit positive charge is sometimes called a test charge. Why? Because it is used as an indicator to find the direction of the electric field. Hence, because of that definition, we say electric lines of force radiate from a positive charge and they end on a negative charge. And as you can see, they enter or leave the charged surface at right angles or normal. Electric flux density. Guys must be able to state the formula for calculating electric flux density, but it is not a problem you are given. The total number of electric lines of force in an electric field, we have defined what electric field is, the space around a charge, and we are saying the total number of electric lines of force in an electric field is called electric flux, and the symbol is the Greek letter psi. This is the symbol for electric flux. Electric flux is different from magnetic flux, please take note. And we are saying since the electric flux is directly proportional to the charge, we need no special unit for electric flux, and we simply state that electric flux is equal to charge, where psi is the electric flux and Q is the charge on each plate. we are now looking at flux per unit area. This is what we call electric flux density, and we are saying its symbol is D. The symbol for electric flux density is D, and it is the electric flux crossing normally per unit area of that section. That is to say, electric flux density is equal to electric flux divided by the area, and the unit is coulomb per square meter. So this is electric flux per unit area.
Factors that determine the capacitance of a capacitor are the area of the plates, the number of the plates used, the distance between the plates, as well as the type of the dielectric used. And how does the area of the plates affect capacitance? The higher the area, the higher the capacitance. And we know that a plate is also known as a conductor, and the bigger the size of the conductor, the more the electrons that it contains. So if you increase the area of the plates, you are also increasing capacitance. And if you decrease the area of the plates, you are also decreasing capacitance. It will become more clear when we look at the formula for calculating capacitance. It will summarize how each factor affects or determine the capacitance of a capacitor.
Let's analyze how the distance between the two conductors or between the two plates affect the capacitance. And we are saying the closer the plates, the higher the capacitance. In other words, we are saying the thinner the dielectric, the higher the capacitance, because the dielectric is put between the two plates or between the two conductors. But we know that it is very difficult to get a very thin dielectric, because sometimes capacitors have got a high working voltage. Because of this, we've got many different types of capacitors. So we are saying a very thin dielectric, we will have also a higher concentration of electrostatic lines of force than a thick dielectric for the same charge of voltage. So we are saying electrostatic field strength is increased as the dielectric is made thinner and thinner. Hence, the distance between the plates affects capacitance. This is an illustration of how plate area affects capacitance. And as you can see, we've got two capacitors connected in parallel, and we've also these two capacitors connected in parallel as well. And we are saying equivalent to two larger plates separated by a dielectric, meaning that the larger the surface area, the larger the capacitance. So instead of connecting two capacitors in parallel, what can you do? You simply use one capacitor but with larger surface area. Hence, we can safely say capacitance is directly proportional to surface area of the two plates. Hence, capacitance increases with increasing plate area. Then, this is an illustration of the effect of the distance in the two plates or between the two conductors. If you increase the distance between the plates, you are, as shown, you are rather decreasing the capacitance by half. So we can safely say an increase in the spacing of the plates, which is represented by D, meaning the distance between the plates, is similar to connection of additional capacitors in series. This reduces capacitance. So we can safely say capacitance is directly proportional to 1 over D, which is another way of saying capacitance is inversely proportional to the distance between the plates. So capacitance reduces with increasing plate spacing. Plate spacing is what we call the distance between the plates. The other factor that affects capacitance C is the type of dielectric. This is also known as type of insulator, and we are saying the dielectric between the two plates or between the two conductors of a capacitor, its function is that it concentrates the electric lines of force or the electric field. And the simplest dielectric that we have is air. And we are saying the ability of an insulating material or the ability of a dielectric to support an electric field and store electrostatic energy is called its permittivity. Guys, you must be able to define permittivity, and this is a measure of how much a material is as a dielectric when compared to a vacuum. We know a vacuum is an empty space, it does not contain matter. We also have what we call absolute permittivity. You must be able to define, and the symbol is epsilon O or epsilon naught. It is used to describe how well a material can support an electric field. We also have another term related to type of dielectric, and it is called relative permittivity. permittivity epsilon r. Its other name is dielectric constant symbol K. And how do you define it? It is a measure of how much better that material can support an electric field when compared to a vacuum, hence the word relative, and we call it relative permittivity. Another type of permittivity that we are going to look at is simply epsilon. Let us go. We've got a table 1.1, and it shows the relative permittivity of various dielectric, and the first one is A, followed by bakelite glass, mica, impregnated paper, polystyrene, and porcelain. This is their relative permittivity epsilon r. Air has got a relative permittivity of 1. Bakelite, it has got a range 4.5 to 5.5, and we are saying the higher the permittivity of the dielectric used, the higher the capacitance. You'll see when we state the formula for calculating capacitance. So we are saying different dielectric materials, as shown on table 1.1, have different abilities to store electrical energy in the form of electric field, and it is represented by the symbol epsilon r, and epsilon is a Greek letter. Fig 1.7 shows a mod-plate capacitor. It has got many plates and many dielectric. This is a dielectric. This is a plate. This is a dielectric. This is a plate. This is a dielectric. A plate, dielectric, a plate, a dielectric, a plate. So we call it a multi-plate capacitor. It is used to increase the area of the plates or area of the conductors. Hence, the number of plates also affect capacitance. Let's have a look at the formula for calculating capacitance C. And as you can see, the higher the number of N, the higher the value of capacitance. Hence, the number of plates affect capacitance from that formula. Guys, you must know this by heart. And we are saying epsilon r times epsilon naught times the area of the plates multiplied by the number of the plates minus 1 divided by the distance between the plates give us the capacitance C. So you can easily summarize the way how each affects capacitance from that formula. As you can see, if D is high, it means that C is going to reduce. If A is high, it means C is going to be high. If these two are high, it means also C is going to be high. So we can safely say, insofar as number of plates is concerned, capacitance is directly proportional to the number of plates N minus 1. We saw this formula in the previous slide, and it represents a multi-plate capacitor. What is dielectric strength? This is the ability of the dielectric or the insulating medium to resist its breakdown when the voltage across it is increased. You will see that each capacitor has got a working voltage, and if it is exceeded, it means the dielectric is going to be punched through. And the ability of the dielectric or insulating medium to resist its breakdown is what we call dielectric strength, and various insulating mediums, they've got different dielectric strength. And dielectric strength depends on, one, the strength of the material, the presence of air pockets in the material, the type of material that is used, the size, thickness, and also the shape of the dielectric. The moisture content of the material also affect the dielectric strength. Then last but not least, the size and imperfections in the molecular arrangement of the material also has got a bearing on the dielectric strength. We are revisiting capacitance. Why? Because we've got an important formula which you must be able to apply. And we are saying C mathematically can be defined as C is equal to Q over V, where Q is the charge and the unit is farad. This means that C is also, or charge rather, can be found by multiplying capacitance and voltage. So we can safely say charge of a capacitor Q is proportional to voltage. Hence, the amount of charge Q that a capacitor can store depends on the applied voltage. Don't worry, you'll meet another slide where we will look at how a capacitor charge and discharges. The term C is defined as the capacitance of the capacitor. So this is a mathematical definition of capacitance, and its unit is farad. By definition, the capacitance of a capacitor is 1 farad if it stores 1 coulomb of charge when the voltage across it 1 volt. This is another definition of capacitance. The capacitance of a capacitor is 1 farad if it is stored 1 coulomb, if it stores 1 coulomb of charge when the voltage across its 2 conductors or 2 plates, 2 terminals is 1 volt. But as I said, farad is too large a unit, hence you realize that we use microfarad 10 to the power minus 6 farad. We also use picofarad 10 to the power minus 4 farad to represent capacitance. The larger the value of C, the more charge that the capacitor can hold for a given in time, since we know that Q is equal to CV. Guys, you must know this by head or by heart, whatever is easier for you. We said a capacitor stores electric energy in its electric field. Hence, we want to find the formula for calculating energy stored in a capacitor. We will not derive it, but it is also possible to derive it. And we are saying energy stored by a charged capacitor is related to the value of the capacitance and the square of the voltage across that particular capacitor. That is to say, energy, the symbol W, capital letter W, is equal to half CV squared, as stated above. It is related to C and the square of the voltage. Guys, you must also know this by head or by heart, whatever is easier for you. And where E is energy in joules, C is capacitance in farads, and V is the voltage across the capacitor in volts. This is the way how you can calculate the energy stored in a capacitor. Simply half CV squared. A relook at permittivity of free space epsilon or. What is this? We are saying when an electric field exists in a vacuum, you know what a vacuum is, then we say the ratio of the electric flux density. Electric flux density simply means the electric flux in a unit area, and we are saying the ratio of the electric flux density to the electric field strength. We looked at the electric field strength, also known as electric intensity, is a constant, and this is equal to 8.854 times 10 to the power minus 12. Guys, normally you are given in an exam, but if you are not given, you must know this by heart. And we are saying this is known as the permittivity of free space. We normally, since a vacuum is a well-defined condition, it means that the permittivity of free space is normally used as a reference or datum value. That is, we compare it with the permittivity of all other dielectrics. This is a similar measure to using the earth potential as the datum for measuring voltage. Normally, in electronics or even in electrical engineering technology, earth is the reference value. You measure the voltage at a point with respect to the ground, which is also known as the earth. Hence, permittivity of free space is used as a reference when we are measuring the permittivity of all other dielectrics. In capacitors, we've got what we call relative permittivity, represented by epsilon r, as alluded to in the previous slide. And we are saying it is defined as the ratio of the capacitance with a certain dielectric to the capacitance with vacuum as the dielectric. Hence, we can simply say epsilon r is equals to C2 divided by C1, where C1 is the capacitance of a capacitor with the vacuum as the dielectric, and C2 is the capacitance of a capacitor with another material as the dielectric. Please take note, we are comparing the capacitance of a capacitor with a certain dielectric when compared to the capacitance of a capacitor with the air as the dielectric, hence the R standing for relative. And as we saw in table 1.1, dry air is the same effect as a vacuum and its relative permittivity is 1. The SI unit of charge is 1 coulomb and that of voltage is 1 volt. Therefore, the SI unit of capacitance is coulomb per volt, since we saw that C is equals to Q over V. And coulomb per volt is also known as F in honor of Michael Faraday. We'll be looking at electromagnetic induction, which is attributed to Michael Faraday. So we are saying 1 farad is equal to 1 coulomb per volt. And take note of this italized statement. It says a capacitor has got a capacitance of 1 farad if a charge of 1 coulomb accumulates on each plate when the PD of 1 volt is applied across the plates. We saw it in a slide before. 1 farad of capacitance is contained if a charge of 1 coulomb accumulates on the plate when a PD of 1 volt is applied across the 2 plates. Electric flux density. Guys must be able to state the formula for calculating electric flux density, but it is not a problem you are given. The total number of electric lines of force in an electric field, we have defined what electric field is, the space around a charge, and we are saying the total number of electric lines of force in an electric field is called electric flux, and the symbol is the Greek letter psi. This is the symbol for electric flux. Electric flux is different from electromagnetic flux. Please take note. And we are saying since the electric flux is directly proportional to the charge, we need no special unit for electric flux, and we simply state that electric flux is equal to charge, where psi is the electric flux and Q is the charge on each plate. We are now looking at flux per unit area. This is what we call electric flux density, and we are saying its symbol is D. The symbol for electric flux density is D, and it is the electric flux crossing normally per unit area of that section. That is to say, electric flux density is equal to electric flux divided by the area, and the unit is coulomb per square meter. So this is electric flux per unit area. You will understand capacitors when we do some calculations, and we've got two worked problems in that slide. And the first one goes, two parallel plates of dimensions 30 millimeters by 20 millimeters are oppositely charged to a value of 50 millicoulomb. Calculate the density of the electric field existing between the plates. This electric density is what we call electric flux density, and it is equal to psi divided by cross-sectional area A. We say psi is proportional to charge. Hence, we are simply saying the flux density D is equal to Q over A. Hence, our Q is 50 millicoulomb, which is 50 times 10 to the power minus 3, divided by the cross-sectional area. Please take note that the cross-sectional area must be in square meters. Hence, we are going to change these 2 square meters, and this is 600 times 10 to the power minus 6. Hence, your electric flux density is equal to 83.3 coulomb per square meter, and you are done. Let's go to the second problem, and it goes, two parallel metal plates, each having a cross-sectional area. Please take note the cross-sectional area are charged from a constant current source of 50 microcoulomb for a time of 3 seconds. Calculate the charge on the plates and the density of the electric field between them. This is what we are given. And we are saying, how do we calculate charge? Charge is equal to IT. Hence, we have got our current, that's 50 microamps, and we also have our T, which is 3, and if you multiply the 2, you get 150 microcoulomb. Let's go to the second part, which requires us to calculate the electric density. Electric flux density, this is equal to Q over A. Our Q we are given, or we have calculated rather, and it's 150 microcoulomb, and our cross-sectional area, this must be converted to square meters, and that's 400 times 10 to the power 6, and we get an electric flux density of 0.125 coulomb per square meter, and we are done. More on calculations question. Two parallel plates separated by an airspace of 4 millimeters means that the dielectric is A and the distance is 4 millimeters. This must be converted to meters, and it's 0.004. And the charge across the two plates is 0.2 millicoulomb, and the charging voltage is 125 volts. So calculate the electric field strength between the plates. Electric field strength, also known as electric intensity, is E. E is equal to V over D. So it's simply 125 volts divided by 0.004, and you are going to get 31.25 kilovolts per meter. The second question, B, asks us to find the cross-sectional area. Cross-sectional area of the field between the plates. We are given flux density is 15 coulomb per square meter. Take note, this is per square meter. And how do you proceed? We know that D is equals to Q over A, so we simply make A the subject of the formula. This is our area in square meters. So our Q, we are given 15 coulomb per square meter. Sorry, 15. We are given D 15 coulomb per square meter. And what's our charge? Our charge we are given at 0.2 Coulomb. So we simply say charge divided by electric flux density, and this is going to give you 13.33 times 10 to the power minus 6 square meters, and this can be converted to millimeters, and it's 33.33 square millimeters. This is how you calculate the cross-sectional area. Then the last part, the capacitance of the capacitor, C is equals to Q over V, and we've got our Q, that's 2 times 10 to the power minus 4, or 0.2 times 10 to the power minus 3 divided by 125. This gives you a capacitance of 1.6 microfarad. This is how you are going to proceed there. Practice, practice, practice until the formulas get inside of you. Another question on calculations. A capacitor is made up of two parallel plates of dimensions 3 centimeters by 16 centimeters. This enables you to calculate cross-sectional area, and it is separated by a sheet of mica 0.5 millimeters thick. This enables you to find D, which is the distance between the plates, since this is a dielectric, and of relative permittivity 5.8. Calculate a capacitance. If it is not a multiplate capacitor like it is, you simply see is equals to epsilon naught epsilon r multiplied by the cross-sectional area, all divided by the distance between the plates, which is D, and we are going to convert this to meters. It's 5 times 10 to the power minus 4. Our epsilon naught is 8.854 times 10 to the power minus 4, and we are given the cross-sectional area. I omitted something, guys. Can you correct this? This must be 5.8. I don't know what happened. Then the cross-sectional area, 6 square centimeters converted to square meters, is 6 times 10 to the power minus 4. And take note that you must get 51.62 picofarads. Then we are also required to find the electric field strength, also known as the electric intensity, and this is simply V over D. We are given our D is 200 volts, and our D is equal to 5 times 10 to the power minus 4 meters. If you divide, you are going to get an electric field strength of 400 kilovolts per square meter. Can you correct accordingly there? It must be 5.8, and see if you can get this. One of the objectives says you must be able to describe capacitor action, and this is what we are doing in this slide. We have got this is a schematic diagram, and this is a capacitor. It has got two plates X and Y. It also has got a galvanometer which measures small currents when they flow. And how does it do that? It deflects when current flows, showing the amount of current flowing. Then we've got a contact switch. This is a switch that closes, allowing current to flow, and opens, stopping the flow of current. Then this is the source of EMF. So what happens is when we turn on the switch and also off, is what we call capacitor action. So we are saying, consider a capacitor formed by two flat metal plates X and Y, and facing each other and separated by an air as the dielectric, or even any other insulating material as the dielectric. Please take note that there is no conductor between X and Y, because there's an insulating material between the two, and we call such a capacitor a parallel plate capacitor. And please take note that we've got electron flow of current and conventional flow of current, and conventional flow of current is shown by this arrow, and it says current flows from positive to negative. So this is what happens if you turn on the switch. The positive terminal of the battery is going to attract electrons, because we know this is a conductor, because a conductor has got many free electrons, so it is going to attract electrons, and they are going to flow in this direction, pass through the battery and to the negative terminal of the battery before proceeding to the Y plate. As a result, plate X is going to be deficient of electrons, while plate Y is going to be in excess of electrons. Hence the charge on the top plate becomes positive as shown, while the charge on the negative terminal plate becomes negative. In other words, we have formed a battery, we have formed a cell. So we are saying this is a growing electric field. So after a while, there's going to develop an electric field. These lines represent electric field between the two metal plates. Hence, they flow from positive to negative, as we saw. And these are the ends that are connected to the metal plates. And we call this a charged capacitor. So we are saying, when plate X is closed, the positive terminal of the battery attracts electrons from plate X. They pass through the battery to its negative terminal, and the negative terminal is going to repel electrons to the bottom plate X. The effect is that plate X becomes positively charged, as I said, while plate Y becomes negatively charged. In other words, it is going to charge to the terminal or to the EMF of the battery. More on capacitor action. We are saying after a while an electric field builds up between the two plates, that is X and Y, and we are saying that process whereby the potential difference across the plates X and Y develops is what we call charging of the capacitor, and the voltage across it will after a while acting as a counter EMF, in that it will start opposing the voltage from the battery that is charging it, and as soon as the voltage across the capacitor is reached the battery voltage, the flow of electrons or the charging current is going to stop. When that has happened, we can afford to disconnect the two plates of the capacitor from the circuit, and it will remain charged for a long time depending on the dielectric used. In other words, we are saying it stores electrical energy and we can regard it as a reservoir of electricity. If we now want to discharge the capacitor, or if we connect a conductor across the two plates X and Y, the galvanometer is going to show a momentary deflection, or it will measure the amount of current flowing in the circuit, but this time it will be in the opposite direction to the one it measured when the capacitor was connected to the battery. Why? This is because electrons are now moving from X to Y. When the battery was charging, or when the battery was connected, it was moving from X to Y through the wires, and when this is happening, we call the capacitor is discharging, hence energy stored is released. This is what we call capacitor action, charging a capacitor and discharging a capacitor. Just like resistors, capacitors can be connected in series and also in parallel. We are now looking at how to find the equivalent capacitance of capacitors connected in series, and we are going to derive. But for the sake of the exam, you might not be required to derive. You are required only to state. Right, these are three capacitors connected in series, one after the other, and this is the equivalent capacitance made up of one capacitor. So we want to find the equivalent capacitance. Three capacitors have the same charge of Q. So we are saying the charge on C1 is equal to Q, on C2 is equal to Q, and also on C3 is equal to Q. And how do you find charge? Charge is equal to CV. So we are saying Q is common. So Q is equal to C1 times V1, and it is the same as C2 times V2, and it is also the same as C3 times V3. But we know that V1 is equal to Q over C1, V2 the same Q over C2, and V3 is equal to Q over C3. And we are saying if an equivalent capacitor stores the same charge, then when applied with the same voltage, then how do we find C equivalent? Simply Q over V, or V is equal to Q over equivalent capacitance. Let's proceed. We are continuing with finding of total capacitance of capacitors connected in series. We know that for the series connection in the previous slide, V is equal to V1 plus V2 plus V3, which is the voltage across a series circuit. And equivalently, we can say, how do you find V? V is equal to Q over C. So we can say V is equal to Q over equivalent capacitance, and this is equal to Q over C1. This is equal to V1, Q over C2, V2 plus Q over C3, which is equal to V3, and we can divide by Q throughout, and it will be 1 over equivalent capacitance, which is total capacitance, is equal to 1 over C1 plus 1 over C2 plus 1 over C3. Please take note, this is the formula for calculating total capacitance or equivalent capacitors when capacitors are connected in series. It's like resistors connected in parallel. Please take note. So for any connected capacitors connected in series, for any capacitors connected in series, total capacitance is equal to, as shown, 1 over CT, which is total capacitance or equivalent capacitance, equals to 1 over C1 plus 1 over C2 plus 1 over 3. So after finding this, to find equivalent capacitance, you simply say 1, you find the reciprocal of this, and there's the reciprocal also of this. So it is same as any resistors connected in parallel. But for only two capacitors connected in series, just like two resistors connected in parallel, it's C1, C2 divided by C1 plus C2. Please take note of this. Capacitors can also be connected in parallel, so we want to find equivalent capacitance for capacitors connected in parallel. We've got C1, C2, and C3, and the charge on C1 is Q1, on C2 it's Q2, and also on C3 is equal to Q3. But the voltage across the three capacitors is the same according to the properties of a parallel connection, and it is equal to E. We want to derive the formula for capacitors connected in parallel, but please check note, for the sake of your examination, you might not be required to do this, but only to make use of the derived formula. Hence, we can say the charge on Q1 is equal to C1V, the charge on Q2 C2V, and C3V being the charge on Q3. And we are saying since V is common in a parallel circuit, the total charge drawn from this supply voltage is equal to Q1 plus Q2 plus Q3. All this charge is coming from the source of the charge, which is equal to Q. We know that Q is equal to CV. Hence, we can say the total charge CV is equal to C1 times V, C2 times V, C3 times V, since V is common, and we can afford to divide throughout by V. And for capacitors, for the three capacitors connected, C1 is equal to C is equal to C1, C2 plus C3. That is, we simply add the capacitance of each capacitor. Hence, this is the same as we do when we are finding equivalent resistance of resistors connected in series. Resistors in series, R1 plus R2 plus R3. Capacitors in parallel, C1 plus C2 plus 3. Hence the statement. This result is exactly the opposite in form to that for resistors in parallel. It is voltage that is common and not charge. Please take note. We are now going to derive capacitance formula, and we are starting from epsilon is equal to electric flux density divided by the electric field strength E, and this is what we call absolute permittivity of the dielectric, and it is equal to epsilon O plus epsilon R, and it is measured in farads per meter. We have just seen that a dielectric other than A is more effective than a vacuum by a factor of epsilon R times. So the absolute permittivity is given, as I said, by epsilon R times epsilon naught. But we know that electric flux density D is equal to charge divided by area, and we know that electric field strength is equal to voltage divided by distance. So as we saw, epsilon absolute permittivity is equal to Q over A times D over E. But we know that C is equal to Q over V. So we are now replacing charge. We can say epsilon is equal to CV divided by A times, this remains D over V. If we simplify, we are going to have epsilon is equal to capacitance times distance between the plates divided by a cross-sectional area. If we make C the subject of the formula, it's going to be C is equal to epsilon multiplied by cross-sectional area divided by the distance between the plates. But we know that epsilon is equal to epsilon R plus epsilon naught. So the formula for capacitance is equal to epsilon R epsilon naught times the cross-sectional area divided by D, and the unit is farad. This is what you must know. This is what you must know, guys. I said before, the electrical engineering technology has a lot of formulas which you must know by heart. So we've derived the formula for calculating capacitance. Another problem worked out for you. The question goes, the flux density between two plates separated by mica of relative permittivity 5 is 2 microcoulomb per square meter. Find the electric field strength between the plates. How do you find electric field between the plates? Is simply electric flux density divided by absolute permittivity, and absolute permittivity is equal to epsilon naught times epsilon R. Hence, we are going to substitute the values. Take note, you must get 45.2 kilovolts per meter. Then this one is for you to do on your own, and please take note, you are required to find, there's a hint there for you. You are required to make D the subject of the formula, and your solution must be 0.4 millimeters. And the question is, a waxed paper capacitor, which means this is a dielectric, has two parallel plates, each of effective area 800 square centimeters. This must be converted to square meters, and we are saying the capacitance is 4,425 picofarads, and we are saying determine the effective thickness of the paper, and we are saying the thickness of the paper is equal to the distance between the plates D, and you are given the epsilon R is equal to 2.5. Do that on your own, guys, and make sure you get 0.4 millimeters. This is the last slide on capacitors, and guys, we are done, and we are finishing by looking at dielectric absorption. What is dielectric absorption? We are saying when a capacitor is discharged by shorting the two plates or the conductors, it should have a 0 volts when we remove the short circuit. However, you realize that atoms sometimes remain partially polarized, and when the short is removed, they cause a residual voltage to appear across the capacitor, and we call this dielectric absorption. So it means that dielectric absorption is when a residual voltage remains in the capacitor after even discharging it to 0 voltage by shorting the two plates or the two conductors. Why? Because we say atoms that make up the material, they remain partially polarized, which means they don't completely discharge to 0. And in electronic circuits, the voltage due to dielectric absorption can upset circuit voltage levels in TV tubes and in electrical power apparatus, and can result in large and potentially dangerous voltage. This is the end of our presentation on capacitors, and I hope you have liked, I hope you have subscribed, and also to share this video and even to comment. Guys, this is the time to say bye-bye insofar as electrical engineering technology capacitors is concerned. We are done. Our next topic will be on electromagnetic field theory, and it's quite long. So, for you not to miss more and more of these tutorial videos on your favorite channel, Telecom Acad, don't forget to like, don't forget to subscribe, and also to share. Until we meet again, guys, take care of yourself, and I'm out.